We are looking at, or at least my goal is, to get as much practice at using the chain rule as we can. So I have a big chunk of questions we're going to get done. And so I'm going to dive right in. In a technique like the chain rule, just looking at this list, do you see how varied they are? Every single one of these questions involves the chain rule, but they all, well, a lot of them look totally different from the next guy, right? So the chain rule is a very powerful, very versatile process, and it allows us to differentiate functions of functions. And one of my other, somebody in my other class said, well, how do you know it's a chain rule and not just something normal? So here's a very, very rough rule of thumb. If it ain't an X, it's a chain rule. So what the heck do I mean by that? If that was sine X, it wouldn't be the chain rule, right? But it ain't an X, it's an X squared minus X, so it's a chain rule. That square root has a 4x squared minus 5 in it. That makes it a chain rule. If it was just an X, wouldn't that be 1 over the cube root of X, and you could do it in the usual other ways, right? You would call it X to the negative a third probably. If I said to you that that was just cosine X instead of cosine X cubed, in this case theta, do you see that cosine pi t? That makes it a chain rule. See this e to the ax and the cosine e bx, that makes these chain rules. Ain't an X. Sine of X squared, chain rule. Big ugly fraction to the power of 5, chain rule. Big ugly fraction inside the square root, chain rule. So if it ain't an X, it's a chain rule. Right, so if you see a sine X or a square root of X or something like that, you're probably not going to be doing a chain rule on it. So let's get started, our first fella. Covered things like this yesterday. Actually covered quite a few of these yesterday, but the more practice, the better. Okay, I look at this and I see the sine of something. So when you differentiate it, you get the cosine of something followed by the derivative of the something. And then you make it look pretty. In this case, you can't really do that much except rearrange the order that you write it. Nice straightforward chain rule, right? Nothing much happening. This is also a chain rule. If this had been 1 over the cube root of X, right, wouldn't you still have to write it as a fractional power? Right, if you're going to differentiate it, square roots, cube roots have to be written as fractional powers. So this fella here is going to be written as negative a third. Are you happy about why that is the same thing as that? You cool about what I just did there algebraically? Right. So this is something to the power of negative a third. So you want its derivative multiplied by the power and reduce the power by 1. Finishing with the derivative of the something. Now, calculus is finished here, but the question isn't. We have style points now. We have to try and do our best to make this look as pretty as we can. So I'm going to call it negative 8x on the top. And on the bottom, I'm going to do 3 lots of 4x squared minus 5 to the 4 thirds. Are you comfortable about where the negative x and where the other pieces fit? Right, this is just moving things around. Now that's better, but it's not quite what we want. Don't we want it to look like the original? So it's going to be 3 the cube root of 4x minus 5 to the power of 4. And that's us finished. Now you are going to meet up with some trig functions, you know, tan squared, cos cubed, that kind of thing. Here we've got 3 cos cubed. To realize that what you have is a chain rule, you kind of have to think of it, and I would definitely write it like that. That's the same thing as that, right? But when I'm writing it like that, can you see it's not theta cubed now, right? It's a something cubed, right? It ain't a theta. So the power rule and the chain rule. Multiply by the power, reduce the power by 1, right? So something cubed gets you 3 something squared times the derivative of that something. Well, the derivative of a cosine is a negative sign. And if you rearrange the order and turn that back into a cos squared theta, you're good. Oh, by the way, when you do questions like sine squared and cos cubed in theta, I believe you have to do it like that, right? You have to stick a bracket around it and make a square, because I don't think WebAssign recognizes that if you type it in. If anybody's, it does recognize it?
It works. You have to go back outside of the parentheses it automatically makes and do it, but it will work.
Okay, so you if you play about with it, you can make it do a cos squared. Like, so I guess you just have a few shots at it and you'll figure out how to do it. I'm trying to think what you mean by back out of it. So you type cos, and
It
then you move to,
automatically, you know how it automatically makes the parentheses afterwards,
yes,
so you can just put it in. You type whatever you want in the parentheses.
right? Oh, I lost the rest of you, Jesse.
Was it my internet?
No, you might have, I don't know what it was. I disappeared. So you got to the part where you type in cosine. So what would happen is that you type in cos and then you'd suddenly get these brackets appear, right?
Yeah. And then you just have to move and put the square before the brackets.
And then type the rest there. Gotcha.
Yeah.
Yeah, we've all learned something. 4. W is 3t squared cosine pi 2, pi t. Do you look at that guy? I hope you see a product rule. This will be my f, and this will be my g. And that's good because it is a product rule. That's the right thing to do. So it's going to be f dash g plus f of g dashed. And if you differentiate this guy, you get 6t, and you leave this guy alone, you get cosine pi t. And then you leave the f alone, which is this guy. And now you get to the cosine of pi t. The cosine of pi t is a chain rule. It's the cosine of something. So when you differentiate the cosine of something, you get negative the sine of the something times the derivative of the something. Are you all happy about where that times pi is coming from? It's the derivative of pi t. And now we're into style points. If you look at these two expressions, is there any common factor that you could pull out?
Three t.
Agreed. That leaves you with 2 cosine pi t's, a negative, used up, t left over, pi left over. And we'll call it good. Okay, let's look at this guy. Hopefully you all recognize Another product rule. This product rule is going to involve differentiating e to the ax, and in some places differentiating cosine of bx. Do you notice that both of these are little baby generals? If it was e to the x, the answer would be just e to the x. But since it's e to the something, right, it's going to be a little bit different, just a tiny bit, but enough to make a difference. Right, differentiate e to the ax. I think of that as e to the something. So you get e to the something times its derivative, and then leave the g alone. Leave the first guy alone. And the cosine of bx, because remember, x is a variable, b is just a constant, right? A, B, C's tend to represent, they're just fixed numbers, right? So b is like 2 or something. So if you want to differentiate the cosine of something, you get negative the sine of the something times the derivative of the something. And what's the derivative of bx?
B.
Yeah. So, style points. Is there any common factor that you can see that we could pull out from both these terms? Any common factor?
We got e to the ax.
So I see.
Question mark?
Yeah. So you're going to have a cosine bx minus b sine bx. Call it good. It's amazing how many different things the chain rule can work with, right? Even although we're about halfway through this, right? There's a lot of variation in all these questions, what they look like. Our next film. Yet another product rule. There's F, there's G. You want its derivative is F dash G plus F of G dash. Nothing too spectacular. Now, do you notice that this guy is going to need the chain rule? Isn't this going to be something to the 5 and this guy's going to be something else to the 10? So here goes. If you differentiate something to the 5, you get 5 somethings to the 4 times the derivative of the something, which is in this case 3. And then you leave the G untouched. Now you leave the first guy, the F, untouched. And you differentiate this mess. 10 somethings to the power of 9 times the derivative of the something. Okay, style points. Look at these two terms, this combination here, this combination here. Let's go hunting for common factors. There's quite a few this time. Anything from here and here that you could pull out as common factors?
There's 3x plus 3.
I agree. There's a 3x plus 3. What power can you pull out? Three x plus 3 to the power of what?
4.
Yes. Okay. Anything else? because there is.
X squared plus 2x,
Kind of power can you do for that one?
9.
That gets a little bit harder, but keep looking. Is there a number we can pull up?
5.
Yeah, I think that's everything. Let's see what we got left. Used up, wasn't used up, one of these left. So I have 3 lots of x squared plus 2x. Plus, well, 10 uses up, so there's 2 left over. What else have I got? One of these. Used up, and one of these. So it's getting nicer. Every step gets a little bit closer. Just going to distribute that and see what we get. 3x squared, add 6x. 5 times, is that 5? 3. 3 times 2 is 6, that's 12x squared. 3 times that is 6, 3 times that is 6, 12, double 12, that's 24x. And 3 times 2 is 6, and then double it, you get 12. Those guys get you 15x squared. Those guys get you, what, 30x and a 12. Okay, anything you can do with this quadratic? Could you pull out a common factor, for instance? Any common factor out of this quadratic? Yeah. So what did you say again, sorry?
3.
So you got 15 of these now, because you're pulling out a 3. And 3 times 5 is 15. And that leaves me with 5x squared plus 10x plus 4. 5 and 1, 4 and 2, 2 and 2. Not, that's as good as it gets. We are done. There was a lot of making it look pretty here, wasn't there? A lot of writing just to get to that point. Right. You look at this question, I hope what you see is a fraction, which means it's a quotient rule. Also, the top guy, the sine of x squared, when I come to differentiate it, won't I need to do the chain rule on that guy? So it's a quotient rule mostly with a little chain rule tagged on as a bit of extra. So let's see what we get. You get f dashed, which is the derivative of sine of something. Well, that gets you the cosine of something times the derivative of something. And then you leave the g untouched. Take away, leave the top guy untouched, and differentiate with g dashed, which is 2x. And you get x squared plus 1 squared. Now I'm going to see if there's anything I can do here. Oh, I can pull out a 2x. So I'll pull out 2x as a common factor, and I'm left with x squared plus 1 cosine of x squared, take away the sine of x squared. I'm not going to do the rest. It's only nitpicking now. I guess I should distribute this, but I'm pretty sure I'm not going to get much else out of it. So this is the guy that's going to give you a headache. Ugly fraction raised to the power of 5. I'm pretty sure that this fraction is going to involve us doing the quotient rule, right? Because fractions do. But the way it's written, isn't it something to the power of 5? Isn't it a chain rule first? So when you do the derivative of this guy, it's something to the power of 5. That's 5 somethings to the power of 4 times the derivative of the something. So I'm not even doing that bit. I'm just writing down what I'm going to do, right? Something to the 5 is 5 somethings to the 4 times the derivative of that something. And that just helps my brain by not trying to do too much at once. So what I can now do is focus on this guy. But this guy doesn't need the chain rule. Isn't this guy just a common old garden quotient rule? Nothing that special about it. So it's going to be f dash g, take away f of g dashed over g squared. Okay, back to this guy. If you differentiate the top, you get 3u squared. You leave the bottom alone. Take away, leave the top alone, and differentiate the g. All over u cubed plus 2 squared. What do you think I'm going to do with this top row here? Because we're on to style points now. Look at the terms on the top. What do you think I'm going to do next?
Factor out of 3u squared.
Okay. Now, if you pull out a 3u squared as a common factor, you're left with a u cubed plus 2. And to save a line of working, aren't you also going to take, leave behind a minus u cubed minus 1, which is essentially a minus u cubed minus 1, right?
Wouldn't that be plus 1?
Did you all catch that deliberate mistake? No, I just made a mistake. You're right, it is a plus 1. Which basically means I get 3, and 3 3s get me 9. Okay, want to make it look pretty. This is something you probably might not have thought of. What I can do is I can combine the bottoms. This guy and this guy get me 45 u squared minus 1, the 4. We are finished. There is a temptation to somehow think that because this is written that way, that that's like it's carved into stone, that you can't do anything to it. But actually, you can break this into two parts. In fact, I could have done that right at the start. Now, if I'd written it this way, wouldn't this have been a quotient rule with some chain rule there? And you would have ended up with the exact same answer. So it wouldn't be wrong to do it that way, just a different way to do it. So a lot of stuff today, and we still have more to go. How are we doing? Any questions? No. The more practice, the better you get comfortable with these guys. That's what I think, anyway. Right. Someone was going to say something there. What was it?
I'd definitely be confused doing that, but yeah.
Yeah. But if you see it a second time, it's a little bit less weird. Well, this is the last one in this set. Are we cool? Now, I can do this question two different ways. Both work. Version 1 is I think of it like that. If I think of it like that, isn't this going to be a something to the power of half and the chain rule happens first? Or I can think of it as that, right? Splitting the square roots and making them half powers. And if I think of it as that, isn't this a quotient rule with some chain rule there? So chain rule followed by quotient, quotient rule followed by chain rule. Do you see how it's two ways of looking at the same thing? Now, since I'm only going to do one of those two, which one would you like to see being done? Because they are both extremely ugly. So it's not like one of them's, one of them's less work than the other. If there was, I would definitely be doing it. So, do you want the chain rule first, quotient rule second, or do you want this one?
First one.
Okay. Then its derivative, it's something to the half. So it's 1/2 something to the negative a half times the derivative of the something. That's essentially the chain rule. Something to the half. 1/2 something to the negative a half times the derivative of the something. And the something, right, this derivative here, is going to be a quotient rule. So I'm also, before I even worry about that, I'm going to fix this. Here's a little trick in algebra. Do you see how that's a negative a half power? Can you imagine that's going to cause problems later on when we do style points? So I'm going to change it to a positive a half power. And I can do that as long as I do the reciprocal of the guy inside. So this is the same mathematically as that. But you see how that's going to turn into a nice square root when we're finished? That's going to be a kind of square root. That's going to be a nice square root. But now, if you call the top f and the bottom g, you've got f dash g, take away f of g dashed over g squared. And this guy is the f, and that guy is the g. So what have we got? We've got 1/2. Might as well turn this into a square root, which is essentially the reason that I decided to do it that way, times. F dashed is a derivative of the top, which is cosine t, multiplied by leave the bottom alone. Take away, leave the top alone. And derivative of 1 plus cosine is negative sine. And everything in the bottom gets squared. If you distribute, you have a cosine t plus a cos squared t. Negative 1 times that guy is a plus sine t. And negative times that guy is a plus sine squared t. And it's still all over 1 plus cosine t squared. Is there anything on the top that can be changed to make it look prettier? There's 4 guys in the top. Do any of them play well together?
Cosine squared plus sine squared is 1.
Right. So how about 1 plus a cosine plus a sine? And we'll call that question done. Right. This is at the tail end of chain rule, right? Ugly functions being being differentiated, right? Not, you don't expect pretty when you do these, right? And that's pretty ugly. So what I want to do now, for the time we've got left, is look at some homework questions. Maybe even do one, especially the last one. And we'll just focus on what method we would use to differentiate it. Right. So we're looking at the chain rule. Question 1. Isn't this just something to the power of 6? Chain rule, nothing special. Wouldn't you call this 9x plus 8 to the power of half, and then it's just a chain rule? Ooh, this one's a bit uglier. How would you rewrite this one so that the chain rule could happen? Because I did one earlier today. What would you rewrite that?
Power of negative 1/3.
And now it's a chain rule, yeah. And wouldn't this guy be 6x plus 1 to the power of what?
-3.
And now it's a chain rule. This guy is actually 5x plus 1 to the -3. Are you okay with algebraically that that is the same thing as 5x plus 1 to the power of -3, in which case it's just a chain rule? Next fella. Would you agree it's just a cosine of something, so it's a chain rule? Cos cubed, sine squared, secant to the 4th, those kind of guys. Think of them as cosine theta with a bracket around it squared, right? We did one of them, actually. I think we did that one in my list, number 3. Isn't this just e to the ugly guy, so it's a chain rule? Isn't this going to be a product rule? But when we come to differentiate e to the -4x, won't that require a chain rule? Right. The derivative of e to the -4x is e to the -4x times the derivative of -4x, which is -4. That's a product rule. When you come to differentiate the sine of pi t, you will get the cosine of pi t times pi. If it ain't a t, right, if it ain't an x, it's a general. If that was sine x or sine t, it wouldn't be a problem, but it isn't. It's sine pi t, right? So there's a little problem, right? We got a general. Done one not unlike that. That would be called r to the half, but it's basically a product rule involving the derivative of that guy. So that's the chain rule piece would be here. Did one like that a minute ago. Wouldn't this just be e to the something? So it'd be a chain rule. So it'd be e to the tan theta times the derivative of tan theta. Done one ugly guy that looks like that. Done an ugly guy that looks like that. Wouldn't this be e or something? So it's a chain rule. And wouldn't the something be the derivative of that fraction? So this would be a chain rule with later on a quotient rule. This would be a chain rule with a later on product rule. Done one like that. Looks like that guy. Product rule. Except when you differentiate the cosine fella, you're going to have a little chain rule going on. Product rule. This guy's going to have a chain rule. So is this guy. For instance, if you differentiate e to the negative x, you get e to the negative x times -1. And if you differentiate the cosine of x squared, you get negative sine of x squared times a 2x. There's ugly guy to power of 3. It's actually a Russian doll question. This guy you would call, let's do this guy. He's weird enough, I think. Sine squared x squared plus 6. I want to differentiate sine squared of x squared plus 6. Well, to help with the chain rule, think of it as that. Right, it's something squared. So you want its derivative. It's two somethings, technically to the power of 1, which we don't always write, followed by the derivative of the something. I call these questions Russian doll questions, right? Because basically it's going to be a chain rule inside the chain rule. So my next line would be two of these guys. And if you want to differentiate the sine of something, you get the cosine of something times the derivative of that something. So you see it's like the second and then the last shell. Now I want this thing to look pretty. And I'm going to do something that looks weird. How on earth can I turn a 2 sine x squared plus 6 multiplied by a cos x squared plus 6 and rewrite it as the sine of 2 lots of x squared plus 6? What on earth have I just done there? And why is it allowed?
Because you got the formula for sine 2x hiding in there. The x is just complicated.
Yeah, if you think of it as a's, right, where a's could be anything you like, isn't the double angle formula says that 2 sine something cosine the same something can be written as the sine of 2 of those somethings. In this case, the somethings is that. So that's just cosmetic, but you should always put. Or you could leave it as 2 lots of x squared plus 6 if you prefer. So
Also just use the power rule on that one.
Yeah, power rules really only designed for the polynomials, right? X squares, X cubed, X to the halves. There is a power rule thing going on here, but it's a general really, because it's not X, right? It's sine X or sine X squared or something. And that kind of alters the rule a little bit because of that. Right, we're almost done. We've got one more question I'm going to do after this, but let's return back here. Can you see E of that guy is just a chain rule and sine of that guy is just a chain rule? And this is the last guy I wanted to find him. F of t is the tan of a secant of a cosine. This is the ultimate ugly chain rule inside a chain rule. And a lot of people, especially when there's only two terms, see that wrongly as a product rule. If it had been secant t cotangent t, right, or cos t, I should say, wouldn't that be a product rule? But it's not, it's a secant of a cosine of t, right? So that's quite different. So here goes. It's a tan of something. So the derivative is the secant squared of that something times the derivative of that something. So that's one shell of the Russian doll. Oops. Done. Now let's focus on the derivative of the secant of something. What is the derivative of the secant of something? It's one of our 6 guys we should have probably memorized by now. What's the derivative of a secant of something?
Secant times tan.
Okay, so it's secant tan followed by the derivative of something, and the derivative of this is negative sine t. So all I'm doing in this line is rewriting it. I've got a negative, I've got a sine t, I have a secant, a cosine of t, a tan of cosine of t, and I have to finish with a secant squared of a secant of a cosine of t. Whew. That was a load of stuff.